Lowe, who will be talking about constraining subglacial geology with geophysical joint inversions.
Yes, thank you. I'm talking about subglacial geology and how we can maybe infer more information on it with potential field inversion. So starting, the direct information on subglacial geology in Antarctica is limited to areas where, to ice-free areas basically, along the coast and where we have high mountain ranges where we can directly go and look at the rocks, but most of it is hidden beneath the thick ice sheet. And there are multiple good reasons to study subglacial geology. I'm coming from the angle of geothermal heat flow, so we know that a geological unit or rock provinces with a high volume in heat-producing elements can strongly elevate the local geothermal heat flow, and we know that already a moderate increase in geothermal heat flow can drastically increase the Basin melt rates. Also, it can change the rheology of the ice and in a last consequent influence or contribute to the instability of the ice sheet. So I think that's a good rationale to try to study subglacial geology. So if you cannot go there directly and just map it out, what can we do? We can use gravity and magnetic data, and in this study we use a joint inversion approach. So we use the gravity data from AntGG, where we corrected all the masses below the mantle. So we have basically only gravity anomalies related to the crust, and we use the magnetic compilation from AtMap2. And what we're basically doing with the joint inversion is we're inverting a three-dimensional distribution of density and susceptibility in the crust. And then we can calculate the model response and compare that to the observed values. So that's what we see in the second panel, and down here we see the misfit between both of them. Joint inversion geophysics is not particularly new, but the approach we're using, the variation of information, is an approach that got quite popular in the recent years. And we're using the GIF3D academic code developed by Maximilian. And we don't need much math to understand what's going on, but we need just that formula's a bit important. So that's our objective function, which we're minimizing. So basically, we have a three-dimensional mesh, and for each cell, we change this susceptibility and density values to try to, we change that iteratively to try to fit the observed field. And what we have in the objective function, which we're minimizing, is we have the two terms which describe the misfit between the modeled and observed gravity and magnetic field. Then we have two regularization parameters, which basically describe how smooth the model is. And then we have the variation of information term, which basically forces a coupling between both quantities, the density and the susceptibility. And that's because we have the assumption that if we have a geological rock province, or basically a rock that has a susceptibility and a density value, that rock provinces should explain both the gravity and magnetic field. So therefore, we want to have a coupling between both, that we find identical geometries in both models. And you kind of can see already where we're going with that. So that's how we want to infer the subglacial geology then, because one rock type explains both of those quantities. So therefore, we want to couple them. And what we get as a result is basically a three-dimensional cube of susceptibility and density values, and we can slice through them horizontally and vertical slices, and can do cross-section as well. And we already see here quite nicely what the inversion is really doing. So we find in the density and susceptibility model, we find similar structures, but there's no linear relationship between the amplitude. So basically, we have an anomaly here, in low density anomaly here and here, but in the susceptibility, it can have a positive or negative value. So the only constant, or the thing that's similar between both is basically the geometry, or the structural information. What we also incorporate is different boundary condition, which is quite novel, that we use the Curie depth point estimation, which is basically the point at which rocks lose their susceptibility. So below that, you wouldn't expect to have any susceptibility values, but of course you still have density values. So we jointly invert from the top of the bedrock down to the Curie depth point, and then after the Curie depth point down to the Moho depth, we only do gravity inversion, and we get no susceptibility values there, which is quite needy, because traditionally in joint modeling approaches, the Curie depth is set at a constant value of 10 to 15 kilometers, and we have here a way of accounting for variabilities in the Curie depth. I want to highlight in the model two areas. Basically, in the density inversion, we see a really high, long linear feature here along the continent margin, and in the magnetics, we see a really large, high susceptibility value, which is an anomaly which is also seen in the subsection here. Basically, that anomaly relates to density and susceptibility and density values, which are typical for granites. So we started to interpret that's probably an granitic intrusion, probably a batholite. But because we're in the 3D and we can actually cut out all the three-dimensional values, we can pull out those polygons, basically, and look exactly what a certain geometry or certain province has, what that density-susceptibility relationship looks like. So on that map, we see now in gray all the susceptibility density relationship within the model, and the two colorful dots are basically the two different units we have highlighted before, and we can already see that they nicely plot in different regions, which is good. And basically what we can do then is, if we are sure that this area is probably a granite, then we can ask the inversion, find us every location where we have the same density susceptibility relationship, and we can just plot that on the map then. And what we see here is that's the area which we extracted, and it's quite interesting that the same identical geological, same petrophysical relationships are plotting next to it close in the area, which, if I go back here, it's basically that anomaly which in the cross-section looks like it's connected at depth. But here we don't have a connection, but that's because we estimated the standard deviation within that polygon. So we exclude the outlier. So probably if we exclude everything, we would see a connection here. The other thing is really interesting is that we can use geological information where we know what rock types we have. And in red, we see the Granite Harbor intrusive rocks. And I was quite surprised that that bit here isn't plotting, like there's a distinct difference in the petrophysical values that we don't plot that along here. So we came to the conclusion that probably the Granite Harbor intrusive and the possible new, the intrusion we interpreted here are two distinct bodies. Another evidence is that we know the ages of the Granite Harbor, which is Ross aged, and in the Estrada et al. Paper, they found erratics with Sicon ages which date on Pan-African ages, and the source of those rocks are not really clear, so maybe we could infer that it's related here. So basically, we can use then our inversion model to draw sketch maps, and that's the way we probably see it, is that we had a passive margin developing, and then we had a subduction zone which emplaced this large granitic batholite intrusion, which here is connected again, and then we had, in a later stage, either the subduction zone retreated or the subduction zone stopped and a new one developed, and then placed the granite harbor, and then we come to our present-day configuration of two close-by granitic intrusions. That is, of course, highly speculative, but what we really wanted to show is that if we accept that maybe that's an intrusion, or a granitic intrusion, we can look at other places in Antarctica and see that usually granites have a really high heat production. One of the largest or the hottest rocks in the UK are found in Cornwall in a granitic batholite, and the extension of the batholite in Cornwall has roughly the same extent than what we see in the inversion. So yeah, basically what we want to show is that if we don't account for variation in geology, we probably miss quite a lot of contribution to the geothermal heat flow models, and it's really important that we incorporate that. So I skipped through that. Basically, we went also to BGR to actually measure some rocks to get to validate our inversion with real density and sustainability relationships. And we see that that actually quite well works for granites and diorites, but we cannot really reproduce really dense rocks, which probably don't fill the whole volume of our cells. And with that, I want to highlight that subglacial geology might be a really important contributor to geothermal heat flow. But in current models, we don't really account for variation in crustal heat production and geology, and that a way maybe forward is geophysical inversion to at least find those regions where we have a lot of crustal variation, and we should start to incorporate those into the model. And really, geothermal heat flow is a very interesting interface between a lot of disciplines. So geology nor geophysics will solve that problem on their own. We really need interdisciplinary collaboration, and also really talk to the cryosphere and ice sheet modeling and see what different geothermal heat flow models influence the ice sheet. And the last point I want to make is that we have currently quite good continent-wide geothermal heat flow models with the Lösing, Shen, and Stahl model, but the way forward is probably to go on local and regional scale estimates and try to incorporate as many information we have and try to incorporate geological information as well and not rely on one single method. Yes. And with that, I thank you.
Thank you. We've got time for one really quick question.
Thanks, that was really interesting. Did you look to see if there is anything, right, Australia would have been juxtaposed to that portion of Antarctica. Do you see similar structures in Australia that you could physically get samples and look at their content of heat-producing elements?
Yes, that would probably be possible, but then again, there's a lot of variation in different rock types already anyway, so the question is really how representative that would be. You would need to use somehow tectonic maps to trace those provinces into the area, but yeah, if you don't really know what rocks you're expecting beneath the ice anyways, it's hard to choose the correct one. And also, geology is so much, there's a lot of variation in the geology if you go into the field anyways already. Like if you look at one outcrop, you can have different rock types. And if you try to model that with a geophysical model, you have larger volumes, which you try to initialize your model with anyways. But yeah, definitely looking at different rock types from known units would really help.
All right, thank you so much. And on to our last speaker, Jenny Gales, who I believe is remote. Okay. Yeah, our last speaker couldn't make it in person, so